So we're going to finish up the January 2017 exam, Common Core Geometry. So what we have here is one of those volume questions. First thing we have to do is they're not going to come straight out and tell you all the time what the shape is. So the closest shape we have for this candle, it appears to be a cone. So we just have to make that decision as close as we can. Now the height of the candle, they've got 13 centimeters. Let's pay close attention to our units of measure. Their circumference, interesting, at the widest measure. So that's at the bottom. The widest it gets is at the bottom. So we have our base. They didn't tell us the diameter or radius. They actually told us their circumference. So we'll have to work for the, let's work for the diameter or radius. Let's go radius. All right, so 13 centimeters. All right, so two circumference formulas, 2 pi r or pi d. I want to get to the radius, so I might as well use 2 pi r. Now the circumference can be replaced by this 31.416. Okay, and then we're just going to divide by 2 pi. Be careful of this. A lot of things can go wrong here. Make sure you have this in parentheses, or your calculator is set where you have it like this. Because now those TI inspires, you can put this in the top, put this in the bottom, and it'll kind of hold this together for you. So anyway, the 2 pi's will knock out, and this number that comes out of this should be just over 5.0. Yeah, it's essentially 5. All right, so now we've got the radius and how much wax. We have to know that how much wax is it going to take to make this. We have to convert that to understanding its volume. So we want the volume of a cone. Okay, we've got to choose the correct formula from the reference sheet. Okay, the reference sheet is down here. Yeah, volume of a cone. We don't have to memorize that. We just have to, look at the reference sheet and, know when to use it. So here we go. Let's see, 1/3 pi, 5 squared, and 13. And it's all centimeters, so I don't have to worry. I mean, I should check units of measure and just to make sure. What I get out of this is 340.341, and that's cubic centimeters because you have the centimeters for the radius squared, so that's centimeters squared plus or times another 13 centimeters, so it's centimeters cubed. They said nearest cubic centimeter, so it's approximately 340 cubic centimeters. I guess that's it. All right, seems too easy for 4 points. Yep. Justifying your answer does not mean you need to explain. You can get away with, explain, you'd need words. Justify simply means, take them through this process. Math equations is going to be enough for us there. So, okay. Now we move on to the proof. This is one of the worst ones I've seen because there's so many little tricks in it. All right, let's start with the fact they called it a quadrilateral. That does not mean it's a parallelogram. However, this information right here, let's just focus on that. Okay, one of the things I try to teach my students is take apart the diagram and let's focus on, just one piece at a time. So if AB is congruent to CD and the second piece is that it's parallel, what you have is you have a pair of opposite sides parallel and congruent at the same time. That right there is going to be enough to prove, okay? That is going to prove it's a parallelogram. So from that, we have ABCD is a parallelogram. is enough right there. Well, why do I work with that at all? Because to get AE congruent to CF, I am going to need, one way to do it would be to get those two triangles the same. That'd be my best bet. Okay, so that's going to be the easiest thing. Yeah, there's other ways to do it, and then we got to use subtraction postulate. That'll work too. But I saw this. I saw these triangles were going to be reasonable to go get. Okay. Now, to get these angles, which we can eventually get, we would need these two sides parallel, which we don't have. So you got to be really careful when you look for alternate interior angles. Okay, like this. These are the sides we need parallel. We don't have that. We have the other pair of sides parallel. So the way to get this angle and this angle the same is to prove it's a parallelogram first. A lot of work, but there is another way to do this, but this is how I decided. We're going to get perpendicular, so these are the same. We're just going to have to work for that. And again, because this is going to be a parallelogram, we'll get these two sides the same. So we'll get those sides the same and as far as congruent and parallel. So we're going to have to work at this. I'm going to go for this parallelogram proof. All right. So one, like I'd like to say, is that AB is congruent to CD, and AB is parallel to CD. That's because it's given. All right, second thing. The direct conclusion from that is that it is, ABCD is a parallelogram. Okay, and that's because it has a pair of opposite sides that are both parallel and congruent. That is enough to prove that it's a parallelogram. Now, as a conclusion from that, I get that AD is parallel to BC, and I'm going to do this at the same time. AD is congruent to BC. And then that's because, I know this seems weird, a little redundant, but we do have to specify it, because this is going to get us our pair of sides. We're going to use the parallels to get a pair of angles later. So we do have to say this again, because it is a different pair of sides, because opposite sides of a parallelogram are parallel and congruent. Okay, so now we've got our pair of sides. We're going to use the parallel to get this pair of angles. Now, when we do that, make sure that you use a three-letter path. I had a lot of students trip up on this when we took the mock final. They said angle A is congruent to angle C. The problem is which one? There's three different angles we could be talking about there. So you have to specify our three-letter path. I'm going to say angle DAE. Follow that path, and that's this angle right here. Okay, that's congruent to, let's try to coordinate. B should go coordinate with D. Then you go CF. Oops. So it's angle DAE congruent to angle BCF. All right, and that's by alternate interior angles theorem. In case your teachers don't use that, I'll write it out. By alternate interior angles are congruent when parallel lines are cut by a transversal. And that's just playing it safe in case whoever's scoring your exam doesn't accept that. All right, need a little more space here. Now, that got us a pair of angles. Next, we have our pair of sides from up here. This is one of our pairs of angles. We're going to need another one, and that's where the perpendicular comes in. All right, so BF and DE. I'm going to separate that. BF is perpendicular to AC at, let's make sure we get this. What is it? BF is perpendicular to AC at F. And DE is perpendicular to AC. That's going to happen at E, at point E. All right. That's because it's given. Now, as a conclusion from that, we're going to say that angle, first we have to say BFC and angle DEA are right angles. Don't jump to the conclusion that they're congruent even though they are, okay? That's a little bit of a jump, and it could cost us. So let's go through the right, paths here. First, direct from perpendicular is right angles, okay? Because perpendicular segments form right angles. All right, now we can say angle BFC is congruent to angle DEA, and that's by all right angles are congruent. Or you could say right angles congruence theorem, something like that. All right, what did we just accomplish? Oh, the triangles are congruent, so let's get those down. A little more space. All right, triangle, let's get this right. BFC, congruent to triangle DEA by the angle side triangle congruence theorem. Sorry, yes, congruence theorem. Postulate theorem, whatever your teacher uses, is fine. Right? And why is an angle side angle? It's because the angles here, this one and this one are the ones that we used. It's not the side between them. Okay, so don't put the S between the A's. All right, that's kind of how we do it. Then 9, we're going to use that corresponding sides. Okay, let's make sure that those A, E, C, F, good. And that's because corresponding sides of congruent triangles are congruent. Okay, so 6-point question, pretty tough. The reason that one's so tricky is most students get caught on these two angles are congruent, but you've got to make sure that you establish those sides are parallel first. Otherwise, you have the wrong pair of sides parallel to establish that. So just be careful. All right, next one. Multi-step problem. Okay, so basically what we have is a hollowed-out cylinder. Let's start with the cylinder. So you got a hollowed-out cylinder. Okay, quick version of this, when you're, making materials like a lamppost or something like that, to have a solid metal lamppost would be extremely heavy, and you don't need it to be that, strong enough when we cut out a center from it. So you've got this cylinder, right, for the post. And what we're going to do is to try to minimize the materials and lower the cost, we're going to cut out some of that cylinder. Okay. So really, um, you don't need material to fill the whole thing. You're just going to have material that fills the outside of it. Okay, so think. You're going to basically have a larger cylinder, and we're going to cut out the middle cylinder. All right. So first, we're going to take we need the volume of them now for the dimensions. Okay. So the whole diameter here is 53.4 centimeters. Let's be really cautious of all this. Okay. Now we need the radius for our volume formula. Okay. We're gonna need pi r squared h. So we're gonna need the radius. All right. So 53.4 divided by 2, that's going to look like what? 26.7. So r is 26.7. The height is where it's tricky. Uh, this is really nice. So they give us this in 7.5 meters, which is reasonable. You know, you're talking, if you convert that to feet, you're somewhere around 22, 23 feet, somewhere in that range. So that's reasonable for the height of a lamppost. Now, 7.5 meters, we've got to use the same units of measure. Either we change, the radius from centimeters to meters, or the height from meters to centimeters. Let's do that. So 7.5 meters. Some get taught in science just to move the decimal. I want to be careful. So we'll call it like x centimeters. You need to know 1 meter is 100 centimeters. Well, actually, let's look. I don't know if that's something that's given on the formula sheet. No, it doesn't look like it. I mean, you can go back and forth, inches to meters and things like that, to centimeters. But if you didn't know that, if you didn't know the 1 to 100 ratio here, you could always, I guess, convert this way. And it would get close. So anyway, let's cross multiply. It's 7.5 times 100, which, okay, so that would have moved the decimal 2 places. That would have worked too. All right, so we got to scratch that. That's got to be 750 centimeters. You've got to be consistent with your units of measure. All right, so let's get the volume of the outer cylinder, pi r squared h. The radius is our 26.7 centimeters. Square that. Height is 750 centimeters. So the volume of the outer cylinder, you're going to get 16797, 07.49. Okay, some of your calculators came out 1.6 e to the 6th, I think. Yeah. What does that mean? That's scientific notation. You've got to know, either turn that off on your calculator or know how to convert it. Okay? So got to be careful there. Now, the volume of the smaller, the inside part, is pi times, oh, yeah, that's the part I didn't talk about. So it's going to be, if the thickness of this is 2.5 centimeters, the radius for the inside, this is the radius for the outside, radius for the inside is going to take away that, so 24.2 centimeters. So 24.2 squared, and then still the 750. That is going to be 1379881.7. Okay. All right. Still, there's a few ways to handle this right now. We could apply the cost right now, or we could just figure out how many cubic centimeters there is. Let me just do that. So the volume of the post for the cylinder is, we're going to subtract those. It looks like I'm missing a number. No, I got it. All right, minus this 1379881. Okay, so the volume of the post with a cylinder design has a 2998. 25.75. Now that is in, let's not forget, cubic centimeters. Some of you may get a different number because you changed the meters, okay? So you get a significantly different number. That's nothing wrong with what you did, it's just we did it differently. Now, you could get the cost of that right now, or what I did personally was I went and found the volume of the other post, the material, the content um, that makes up the post. And I am then going to subtract that and turn that into a cost. So it's really however you prefer to do it. Okay. So now with this next one, okay, you're going to have this kind of, you're going to have this rectangular prism design. Hopefully this doesn't go that bad. Yeah, that's pretty ugly. Let me try that again. All right. I'm going to have to lay the post down this way. Okay. So basically you got a post like that, and we're going to cut out, you're going to cut it out. Okay, so your post, if you just look at a top-down view, let's just do that. Get a top-down view only of the post. You're going to have it from here to here is going to be 40 centimeters, it says. Now, to have a thickness of 2.5 centimeters, it's a little different than the cylinder. See, we only had to take away the 2.5 once because it was from the radius. Now we're really talking about the whole length. So not only do we have to take a 2.5 off of this side, but it's also off of that side. That's going to be 2.5. That's going to be 2.5. So, all right, we've got a volume or an area of the base. All right, if you look at volume for this, it's base times height, but that B is the area of the base. And this base is a square, so it's going to be, the 40 times 40. So let's see, the volume of the outer, okay, the outer part of the post is actually going to be 40 times 40, and our height, it's still going to be the 750, right? Centimeters. So that's times 750. So the volume of the outer post, outer side of the post, that's going to be 12, what is that? Okay, 1.2 million? Yeah, it looks like that. Okay, that's cm, centimeters cubed. The volume of the inside part. Here's what I was getting at earlier. If you're taking 2.5 off of each dimension, really what you're left with is 35 across. 35 this way. So your base here, right, it's 35 times 35. And when we do that, you're going to get 918750. All right, same thing that we did up there, the volume of the post, you're going to subtract those. And so the volume of the post, using the rectangular prism design, for that one is 281. What happened there? So we got 281, what, 250? And that's centimeters cubed. So, which post is requiring the larger volume? Looks like the cylinder is going to use more. We want to minimize cost, right? So if the post must be the same post, okay. So the rectangular prism is going to save us the money. All right. So that's what we got to talk about here. We're going to save money on the rectangular prism design. All right. The post should be the rectangular prism design. Because it takes less, it needs less aluminum to make. Okay, and we've shown that. All right, the cylinder one, this is the cylinder one over here. The cylinder one takes that much aluminum, and this is your rectangular prism design. Okay, that one takes that much. So we're going to use less aluminum to make it. All right, now it wants how much money will be saved to use the less expensive design. All right, so let's get a difference in how much aluminum is used. Okay, so how much less aluminum? Just going to subtract these. 299825. 299825. 281250. So we're going to save how much aluminum? Looks like 18,575, 749. That's in cubic centimeters. So that's how much aluminum we're going to save. Now the density of it, what do we got here? 2.7 grams per cubic centimeter, and there must be a cost. How much does it cost? Oh, 0.38 per kilogram. Great. Okay, cost is 0.38, so 38 cents for a kilogram. Genius. All right. Okay. So again, for kilograms, you have to know that a kilogram is equivalent to 1,000 grams. So we've got to change one of these. We either change, the kilograms to grams or the grams to kilograms, whichever. Let's just do this. So 0.38 kilograms is to, let's call it x grams, is 1 to 1,000. All right. Oops. Let's see. 1 kilogram is 1,000 grams. Okay. Something is not working out here. All right, sorry, let me back up a little bit. That's a cost or a density again there. Let me just let me do this again. So basically this is 30, that's the cost for every 1 kilogram. Okay. I want to know what's the cost so that's the same as saying what's the cost. It's actually, let's stick with 38 cents, but that's for 1,000 grams. So we can convert this density, or this cost, I should say, right to there. All right. Now, let's also incorporate, so this is a new ratio that we could look at. Now, the density of this aluminum is 2.7 grams for every 1 cubic centimeter. All right. So 2.7 grams for every 1 cubic centimeter. But what we have is this many cubic centimeters. Right? So how many grams is that? So we'll set that up and we'll cross multiply. So we're going to have the number of grams is going to be right here, whatever this comes out. And let's see, what I end up getting is, it looks like 50154.5 grams. All right, so that's how many grams I need. And here's back to this cost factor. So if I have 50154.5 grams. And I want to know how much it's going to cost. Let's flip this. It's 1,000 grams to every 38 cents. Okay. I know this is a little weird. I had to flip this because these are basically, you know, when you have a cost like it's 38 cents per kilogram or it's 1 kilogram for every 38 cents, really is interchangeable. All right, that's what that density is saying. So I flipped it here so that it would work out. You want grams and grams to be corresponding. All right, so now when we cross multiply, you're going to get 1,000 x, right, equals whatever that is. I get, let's see, 19058.71. Now we're going to divide by 1,000, and you get 19.05871. With cost, you've got to get it to the nearest cent. All right, so what is it that we're going to save? Well, we saved this many cubic centimeters of aluminum. It's got this density and this cost per kilogram. We're going to save per post $19.06 per post saved using the rectangular prism design. All right.